Hello, this is take 2. I did the lesson already and hadn't finished it. My video timed out and it was over 33 minutes and I decided I need to make this shorter. Okay, so I'm going to talk a little bit faster, but again, you can pause, rewind, rewatch, etc. Today, Thursday, May 14th. 13th, I believe. I'll go to the video I did first. 13th. Okay. Define conditional probability. Use the formula for conditional probability to answer questions. Rewrite the formula for conditional probability to determine. So you're rewriting this formula to determine the multiplicative law for conditional probability. Use the multiplicative law for conditional probability to answer questions. And that's example 2. So I'll talk about when this is more appropriate than the original formula. Okay, so note to self. Note 1. Conditional probability occurs when the probability of one event is influenced by an event that occurs first. So think about this. So we had the cookie jar. I said initially that we had 5 chocolate chip cookies in a cookie jar containing 20. So if I eat one of the chocolate chip cookies, the probability of me selecting a second chocolate chip cookie is directly influenced by the fact that one has already been eaten. Okay, that's conditional probability. Okay, so an example would be eating one chocolate chip cookie, then wanting the probability of selecting another chocolate chip cookie. Okay, so I mean, we could do this really quickly. So the chances of me eating the first chocolate chip cookie would be 5 out of 20 times 4 out of 19, where 5 out of 20 is the chance of selecting one of the 5 cookies out of 20 in the cookie jar, times the selection of the second cookie, where now I only have 4 chocolate chip cookies remaining out of the 19. So if you want to think about that, so it'd be 5 out of 20 times 4 out of 19. Okay, so if you want to just ponder that, that will be connected to example 2 that we're going to do down the road. Okay, so to find the conditional probability of event B, given that event A has occurred, we use this formula. Okay, so this is the formula. All right, so conditional probability, the probability of getting event B to happen given that event A has already happened is equal to the probability of event A intersecting with event B, okay, divided by the probability of event A. Now, what's important is if A is the event that's already happened, that event A, okay, that's happened is always going to be the denominator in the conditional probability formula. So whatever event has already happened will then determine the denominator, which is already the probability, which is always going to be the probability of event A. Okay, now this formula can be understood in terms of a rate triangle to maybe simplify things. Okay, so that line means divide, okay, and this line means times, okay. So this is, in a sense, the probability of B, given that A has already happened, is equal to the intersection of the probability A intersecting with B divided by the probability of A. Okay, so if I want to know, this is what I don't know. Okay, that's what I don't know. I don't cover it. And it's the probability of A intersecting with B divided by the probability of A, right? The multiplicative law, which is down here, is if I know or if I don't know the probability of A intersecting with B. Okay, so this is the formula used when given a chart, okay, that finds this number here. Okay, so the best way I can describe it is this is the formula that you use when you easily can find the probability of intersection and probability of A. Okay, so this formula is the probability of B happening given that A is already happening. Okay, it's the probability of event B occurring given that event A has occurred. Where this is the probability that both A and B is occurring. So and, that's the word and, which is intersection. So if you say, well, this is sort of like the other unit in 4.3, you would be right. Okay, and P of A is the probability of event A occurring. Okay, so to find the multiplicative law for conditional probability, we rewrite the conditional probability formula and solve for the intersection. Okay, so C, we'll call it the rate triangle diagram. Okay, so if I want to know the multiplication, okay, or the multiplicative rule, it's where I don't know the intersection. So that's when you have a chart. Okay, this is the chart. Okay, so this is the chart. So if I don't have a chart, I want to rewrite the formula using the rate triangle diagram. Okay, so I can use the rate triangle. So this means, so if I don't know the intersection, okay, so if I don't know that, it's equal to the probability of A times the probability of B happening given that A has already happened. It makes intuitive sense to think about this first, followed by that. That has to happen for a condition to arise, right? So I have to pick one cookie, the chocolate chip cookie, out of the cookie jar to then think about what's the probability of getting a second chocolate chip cookie, given that I've already eaten the first chocolate chip cookie. Okay, so try to prioritize this as the first thing in your formula. Okay, now if I didn't use a rate triangle, I would want to solve for that. So I'm going to solve for the intersection, which means I do the opposite of dividing by the probability of A, multiply it on both sides. Okay, and then these cancel out. So then I have the probability of the intersection, okay, equals the probability of A times the probability of B happening given that A has already happened. And then there you go. That's the same as this. Okay, so let's speed this up. Probability that a pass given that the student is male. So this is the B given that A has already happened. Okay, so an A, and I have to move things over because I really don't have a lot of space on my page. Okay, so the probability that I have a pass given that the student is male. Just let's just shorten this to male. Okay, so I just take out that word student is, okay? So it's an intersection of a pass and the male. Okay, so that's B, that's A, that's B, intersecting with A, right? Divided by the male. Probability that you got the male there. Okay. Okay, so to get a probability, you have to have a fraction. So it's the intersection of the passing. So got the passing. Okay, so that's the passing. That's the male. Okay, so where do they intersect? Well, where the pink crosses the yellow. Okay, so the probability of the intersection is 46 over, this is the big divide line, okay, over the total. Now, if we want to know the total here in the sample set, we have to talk about 200. So that's the total in the sample. Now, you can rationalize that, okay, instead of me just telling you. But if we think about passing, you either passed or you failed. Okay, so how many passed? Okay, how many failed? Well, that was out of 200 in the sample. Likewise, how many were male? So the males were here. These were all the males, okay? But the other category were the females. So it was 102 plus the 98 to give you the 200. So the total has to be 200. The probability that you were male, okay, all the males in total were 102 divided by the total in the sample. Okay, so it equals, now, so this probability is the same formula as all of the desired outcomes divided by the total number in the sample, total number of outcomes. Number of desired outcomes being male divided by the total number of outcomes in the sample. Okay, so this is divide. So a fraction within a fraction, 46 divided by 200 divided by 102 over 200. The divide changes to times. You flip the fraction. I'm trying to speed up here because I don't want to run out of video space. So that becomes 46 out of 102, and I think that's divisible, both of them, by 4. Nope. Only divisible by 2. So 23 over 51. Okay? So that's the probability, is the probability that you get a student, that a male is passing. Okay? All right. B. So now you want to get a pass given that the student is female. So pass is the event B, student is female is event A. I'm going to move this over. So the probability that you get a pass given that you have a student is, so just cross that out, female. Okay. Right, so then that's a B given A kind of scenario. So we have to have the intersection, probability of a pass and a female divided by this is the value that's, or the event that's already happened, so it's the probability of the female. Okay, that's B intersecting with A, and that's A, right? Okay. So, got, oh, let's do this. Let's make it simple. So a pass is still pink. Okay, pass is still pink. blue. Okay, so where do the pink and the blue intersect? It's this one, right? So 68 over the 200 divided by the female. So number of total females is 98, right? We don't care whether they've passed or failed. We just care that they're female, okay? So 98 over 200. So that's 68 over 200 divided by 98 over 200. And we know that we invert and change the divide to times. So these cancel out. And then this is 68 over 98. So we're going to try to go for divided by 4, 17. No! 2. I was so hopeful. Okay, so 68. I could have swore that was divisible by 68, 98. $34. Now I'm second guessing myself. 49. Oh, 49. Okay. Okay. So is the probability that a female is passing? Okay, here we go. All right, so I'm going to try to speed up here because I'm at 17 minutes. Oh, not too bad. Okay, so example 2. Find the probability of drawing 2 diamonds in a row from a well-shuffled deck of 52 playing cards without replacing. So this here, that causes a conditional probability. Okay, so if we aren't replacing the first card, okay, then the second card, because we're trying to draw 2, okay, the second card and the probability of drawing the second card that's diamonds is directly influenced because we're not replacing the first card. So in other words, the sample set is going from 52 in our first draw to 1 less, which is 51. Okay. Now, the other thing is that we don't have, since we don't have a chart, okay, we don't have a chart, we're going to use the multiplicative law of conditional probability. Okay, so method 1, I'm going to show you method 1 and method 2. Okay, so method 1 is the multiplicative law. So what is that? Well, that is us not knowing the intersection, but saying the probability of B given A times the probability of A, where we're going to write that first. Okay, so the probability of A and B. So we let event A be the first diamond, and let B, the event B, be the second diamond. Okay? All right. So if we want to know the probability of the first diamond, D, and I'll use intersection, and the second diamond, okay, is equal to the probability of the first diamond being drawn, okay, times, Okay, so that's event A. So this is A union B. That's event A, okay, times the probability of a second diamond being drawn, given that the first diamond is drawn and not replaced, okay? That's not replacing the first diamond drawn. Okay, so we have 13 diamonds, okay, but we have 52 cards in the deck. I'm not going to reduce this, right? This could be 1 out of 4. I'm not going to reduce it. Times, what is the probability of getting a second diamond if I haven't replaced the first? Well, think about the number of desired outcomes. So how many ways can I be happy about getting a second diamond? So there are 12 diamonds left out of 51 cards left. Okay, so 13 times 12. I could even reduce here. Maybe I'll do that. Divide that by 4. So 52 divided by 4 is... No, 52, yeah, it's 13. So divide this by 4 and this by 4, which is 3, okay? So that is 39 over 13 times 51. 663. That would be divisible by 3. So that would be 1, 3 over 2, 2, 1. So if I wanted to, I just could type this in. So 13 times 12 equals 156. And then 52 times 51. And then I could convert that if I wanted to, okay, to a decimal. All right. Method 2. It's using a tree diagram. So a tree diagram looks at 2 options specifically. Us getting the first diamond. Okay, so I'm getting a get 1 diamond. So what are the chances of getting 1 diamond? It's 13 diamonds out of 52, okay? Not getting a diamond. What? I'm videoing. I just had the doorbell and somebody else is going to answer the door. Okay, so... Oh my goodness. Okay, so that would be 39 out of 52. Okay. All right. So then here, what is the chance of getting a second diamond? Okay, getting a second diamond, the chances of getting a second diamond are 12 out of 51. 51. Not get a second diamond. Okay, it's the remainder of this, right? So it's 51 out of, so you just go 51 minus 12. 39. Okay, well, what do we want to do? We want to travel down this, because this is getting one diamond and this is getting the second diamond. So what do we use? We use this and we use this. So the probability of getting 2 diamonds without replacement is equal to 13 out of 52 times 12 out of 52, which were the exact same numbers that we had here. Okay, so 13, we'll do the 13 times 12, 156, and we'll do the 52 times 51, 2652. I think we tried to divide that by 4. Or by 12. Let's see if we can 2652 divided by, let's try 12. So that was 22221 over 156 divided by 12, 13. And these are the same, right? Okay. So is the probability of getting 2 diamonds without replacing the first diamond. Okay, now it's your turn to try the questions. Don't forget about method number 2, because that might be effective.